Hello students, so welcome to this topic called Optical Activity, Stereochemistry. I will elaborate on this slide later on, so don't worry. Now we notice that there are certain things in life that the mirror images are different. Like for instance our hands. We know that right and left hands are not identical because if you try to put your left hand into a glove that's meant for the right hand, you can't slot it in comfortably. So we call them mirror images, and they are non-superimposable mirror images. So no matter how I try to move my hands, it can never be the same. Okay, so all the molecules in the body, in the human body in particular, it is handed. And the handedness primarily arises from the tetrahedrostereochemistry of the sp3 hybridized carbon atoms. Basically here, for example, we have a carbon, that's the black sphere in the middle. Can you see that? Yeah. Tetrahedral 109.5, these angles between the bonds. Look at that. Yeah. So what are the molecules that could have a handedness? Now let's see. When we have a single carbon molecule, CH3X, X could be like any halogens that forms a single bond with carbon. This is not chiral because if you do a mirror image of this molecule, you get the identical molecule. They are superimposable. Likewise, when you have a C2XY where X and Y are different halogens presumably, then you still get the same molecule. Now for the last case, when you have CHXYZ, when all these atoms are different, connected to the same carbon, we know that the mirror image is non-superimposable on itself. Take a look at this model here. Now suppose, you see that from what you see, it is orange, white, green. So what you see now is orange, white, green. So we count. G, O, W goes clockwise, right? And the mirror image of this will be the other way around, which is O, G, W, and it goes anti-clockwise, and they cannot be superimposed onto each other. I believe most of you have heard of this word called the enantiomers. This comes from a Greek word called enantio, and it means opposite. So we understand that stereoisomers are molecules which are not identical to their mirror images, and this comes about whenever we have a sp3 hybridized carbon on an atom that's connected to 4 different substituents. Now the thing is, here we use H here, but it does not necessarily mean that it must be hydrogen. It could be bromine, chlorine, fluorine, and iodine. No hydrogen, but this molecule is chiral. So for instance, lactic acid, also known as 2-hydroxyl propanoic acid, it has 4 different groups around the atom itself: hydrogen, OH, methyl group, and COOH. So that's why lactic acid will have an enantiomer. So the positive one for the lactic acid is found in sour milk, and we found this in muscles, especially when we are having fatigue. The L-lactic acids we only can find in sour milk, but we cannot find in the muscles. So you see something special? It's not like anything that's mirror image for the molecules that you can find in the body. Now how do we check that whether 2 molecules in terms of drawing are identical or not, or are they enantiomers? We have to see. Now in this picture here, the red lines indicate those that are having the bonds on the same plane. So if you're looking at this picture that I'm holding on to, these 2 bonds, where it's connected to both the red ball and the orange ball, they are on the same plane because you see this is my plane which is flat against my hand. So what happens to the bond that's connected to the white ball? You see it's going closer to you, right? It's closer means you see more of it, and that's why you see the black one is projecting outwards towards you. You see more of it. And the one that's connected at the back, you see the green ball here is going towards me, right? So you see less of the bond. And that's the reason why it is hashes. Okay, hash lines. So if I rotate this in this manner, it's the same. White ball still closer to you, green ball closer to me. Do this. Still the same. You see that? So here we have a mirror plane to denote that those images here on the left and on the right, they are enantiomers. You can try to rotate this bond, and then you see that, right? These three are the same, 1, 2, and 3. For instance, we look at the white ball as a hydrogen. We can do some rotation. So right now the red is closer to you. We turn and rotate. Then now green is closer to you and red goes behind. Now orange goes for its turn and I rotate it. Do you see? One more time. So anybody can have his turn to face forward. Right? Show some courage. Another word that you have to understand from this topic, stereochemistry, is chiral. So this word comes from the Greek chie, it means hand. And molecules that are not identical to their mirror images are chiral, and hence they exist as two different enantiomeric forms. Now a molecule which is not chiral, or we call it achiral, take note, this is a single word, achiral molecule. So we do not say a molecule is a chiral. This is a chiral molecule, or this is an achiral molecule. Differentiate them. So a molecule is not chiral if it has a plane of symmetry. So what is a plane of symmetry? Like, you know, our hands is chiral because there's no plane of symmetry here. There's no plane of symmetry, right? No plane of symmetry, not even here in this case. Not my watch. But something that has a plane of symmetry would be maybe the charger here. You see, it is symmetrical, right? So this is achiral. My hands are chiral. This calculator is, yes, it's chiral. This molecule is chiral. This pen stand is achiral because you see a line of symmetry here. Good. So lactic acid, when you draw the molecule out, it has no plane of symmetry, and that's the reason why it is chiral. For propanoic acid, it has a plane of symmetry, and that's why it's achiral. For this kind of molecule diagram, what it means is, right, you align the two bonds on the same plane. So you are seeing this basically, and the two middle ones that you see left and right are forking towards you. You see, going towards you in this manner. So that's why both are your wedge bonds going towards you. Then these two are actually not straight, but just on the same plane is going towards me. You see that? See that? Alright. How do we find a chiral center? Quite easy. Normally, you just look out for a carbon that's connected to 4 different groups, right? And we have to understand that the term chiral can be used to describe two things. One is a center, a particular atom, if the atom is chiral, or it can be used to describe the whole molecule if the molecule is chiral. So let's take a look at the example here. 5-bromodecane. This is the structure. The carbon here connects to a bromine, hydrogen, a butyl group, and a pentyl group. And apparently when you draw it out in a 3D manner, they're all different, and there's no plane of symmetry on this carbon. So that's the reason why this molecule is chiral. For methyl cyclohexane, there is a plane of symmetry passing through the methyl group and through the C1 and C4. Basically, I can cut using a plane, cut sideways, alright, cut sideways, and there's a plane of symmetry, so that's why it's not chiral. For 2-methyl cyclohexanone, it has no plane of symmetry because when we cut this away, we cannot have a mirror image within the molecule, so that's why it is chiral. Of course, you can see that, right? The easier way is to count. Note, this is a carbon. 1, 2, they're different groups, right? And then 3 and 4, you see, go 1 to the left, this carbon number 3 connects to 2 H's. This carbon number 1 here connects to an oxygen, so they are really different, and that's why this position here is chiral. But going back to the methyl cyclohexane, you see that these two have two different substituents first, and then going to the left, carbon number 6 connects to HH. Same for number 2. So you can't decide now, you go a bit further. Hey, same again, same. And then you go down, oh, they reach the same position, so apparently they do not have 4 different substituents on the same atom, and hence it is not chiral. Now note that the carbons here in CH2, CH3, C double bond O, CC double bond, CC triple bond, they cannot have any chiral centers. Reasons because they could be planar, they have a plane of symmetry on them, or they are just not sp3 hybridized. So for this molecule here, example, carbon, which is found in spearmint oil, this is a chiral center. Easiest to see is, right, you just draw a circle here, you see something like Mercedes-Benz, it should be chiral. Let me tell you again, it should be chiral. You got to check one more time. Going left, okay, carbon with CC here, oh, carbon with HXC. This is HXC, so you go further and you know that they're all different, and that's why this is a chiral center. For nucatone, which is found in grapefruit oil, again, first step we look out for all the Mercedes-Benz thing, right? And then you see, they are different, 3 of them connected to different groups. Fantastic. For this slide, you don't have to spend so much time to study very hard, because these are just the technical terms, some background about all this optical activity, which leads to stereochemistry for this module. Now we know that ordinary light, right, is actually a form of electromagnetic wave coming from, visible light region. We have 7 of them actually. Normal visible light, red, orange, yellow, green, blue, indigo, violet. And if we look at the whole spectrum for the electromagnetic wave, we start off with the gamma, then X-ray, X-ray followed by ultraviolet, and then visible light, and after that it will be infrared and microwave, and finally radio wave. Okay, but here we just focus on the visible light part. So these are electromagnetic waves that will oscillate in finite number of planes at right angles in the direction of the light where it travels. Ordinary light passes through a polarizer. A polarizer, you can find this in your household, in your car if you drive, those Polaroids shades. So they are polarizers. So they prevent certain rays from going through the lenses, and that's why you are protected from the UV light. Basically, they have what we call the filters in between here that can filter off some parts of the light, and then only minimum light goes in. And that's why it is a good thing, it's a good advice for you if you are driving at night and when it rains. Even in the daytime, you can wear some shades and it helps you see better, because it minimizes the different refraction, the different refracted light going towards the eyes, and it masks the image that you see in your windscreen. Now, if you're really interested in this topic, right, I have prepared another video that you can always go and watch and see and learn some more information. But here, this is just for completeness, and it would be good to know about a new device called the polarimeter, which is used to measure the angle of rotation of a certain molecule if it is chiral. And you should also know that a solution of an optically active organic molecule is to be placed in the sample tube, and we pass through a plain polarized light through the tube. We call it a polarimeter cell, and we measure the angle of rotation, and then we analyze it and calculate how much of each enantiomer is present inside the sample. So we calculate the angle of rotation, which is called alpha, and is expressed in degrees. Now, the assignment of the direction of rotation, we have 2 names for it. One is called levorotatory. It tells you the optically active molecules that rotates the plain polarized light to the left. So it basically, the polarized light goes through the molecule and then it bends and rotates to the left counterclockwise, and we put down the symbol as negative, like in negative morphine. Dextrorotatory represents optically active molecules that rotate plain polarized light to the right clockwise. So the symbol we use positive to denote it, like plus sucrose. Doesn't mean you add more sugar to your coffee. Rotation. Now the amount of rotation observed in a polarimetry experiment depends on a couple of things. One is the sample concentration and the sample path length. Right, because we have the, just now we mentioned tube, right? The cell. We have different kinds of cell, like shorter one, longer one. So it really depends on the path length of the light. So after that we calculate something called the specific rotation with alpha bracket D. D stands for your sodium D line, the light that's used to generate this ray that passes through your sample. And then we set it and add this wavelength. So once again, if you are really keen to know more about this, you can watch the other video. I will list down this URL here. Please feel free and go and have a look. I will also upload it onto the same multimedia. So this specific rotation is actually a physical constant characteristic of a given optically active molecule. So you notice that, right, if they are enantiomers, the angles are exactly the same, just that the sign is negated. Plus, minus, they swap. Check out these molecules. They are actually chiral. Compounds like penicillin V, number 5, sucrose, Chem4. Do not pronounce this as Chem4. I know there's a lot on Instagram. Chem4. Chloroform. It is not chiral, that's why you see 0 optical activity. Cholesterol, morphine, cocaine, we have some value, so it shows that inside them we have chiral center. Acetic acid, there's no chiral carbon, 0. One of the first experiments in this field was first pioneered by a French scientist called Louis Pasteur. So he discovered in 1848. So he discovered enantiomers in crystalline tartaric salts derived from the wine. And these two salts were actually mirror images and they're non-superimposable. So we denote them as right-handedness and left-handedness. For enantiomers, they're also known as optical isomer. So these are names that you ought to know that they mean the same thing. They have identical physical property like melting point, boiling point. They differ in mainly one property called the direction in which the solution will rotate the plane polarized light. Remember, the angles are the same but opposite in sign. Now for reactivity, enantiomers have the same reactivity with achiral compounds or in achiral environment, that means not chiral environments, but they differ in the reactivity with chiral compounds such as enzymes which are handed or in chiral environment. So you see in this example that, right, imagine the base here, something like a stencil. This is actually chiral. If you throw in the enantiomeric form of this molecule here, it doesn't fit in, so it can't really react. So you see this form shows reactivity, but the other one does not. So that's why you have very different effects. We call it some kind of discrimination against certain kind of molecules, because you see the active sites do not match. It's like a puzzle. You can't fit all the jigsaw right. You can't push it in. The groove must be right. A good example here to demonstrate this is the Parkinson's disease, which if somebody suffers from this, they will have a reduced production of the neurotransmitter called the dopamine. So the human have invented some drugs that's actually able to treat or slow down the Parkinson's disease. They exist in two forms. We call them dopa, negative, or the positive dopa. Now for the negative dopa, we know that it's very effective in the treatment of Parkinson's disease, and because it absorbs in blood, transported to the brain, and converted itself to dopamine, which is over here. But if you consume the positive dopa, it is very bad for your health. Super bad, it's not even effective. Now some people think that if I eat something that's harmless, it's okay, right? But what if it's harmful? This is a classic example of why we should be very careful if you're trying to look into drugs to synthesize something. This molecule here is called thalidomide. You notice that it has a chiral center right here. So these two are enantiomers. Basically, thalidomide was developed by a German pharmaceutical company called Chemie Grüntal, and they had actually 20 years of patent when they were the first company who invented this drug. So they found that it is found that it's a very good effective antiemetic which has an inhibitory effect on morning sickness for the pregnant ladies, and so they put it on sale for the pregnant ladies. But what the company didn't know was that, right, the positive form is the effective sedative drug, but the negative form is teratogenic and can cause birth defects. And this is very bad for the pregnant ladies, because the mothers who give birth, they had kids that had no limbs or they were deformed. They have no legs and feet. It's very sad for them. So at the time they didn't know that the drug could interconvert in the body in vivo and become something which is very harmful. And of course, when they have a mass production, they earn a lot of money from that. They didn't want to destroy this. So what happened was they found a patent in South America. They want to sell all the last batch of drugs as possible. And the packaging that they used was something like this. So on the package of this thalidomide, at one corner, they put this image. They use the image and not words because at the time people didn't really go to school and most of them were illiterate. They couldn't read, so they used image to convey some ideas. So basically they told this. They're trying to tell the consumers that if you are pregnant, do not consume this drug because it's bad. You can give birth to babies who are deformed. But people who saw this, they thought it means that, oh, if you do not want babies, take this drug. So what happened was females or young ladies who thought it was that drug, it is a kind of contraceptive. So what happens is they took this drug expecting there's no baby, and then they spend a night together and they gave birth to deformed babies. Again, very disappointing because they draw this, like a form of shape of a baby, and they put a cross here. That means to some people they thought that you eat this, you have no baby, no matter what you do. But what they're trying to tell them is you should not take this drug when you have a baby. So in life, you should learn how to communicate effectively and not just leave to the imagination of the consumers. One great lesson learned. So that was before Germany was unified, and in Western Germany, almost 10,000 of them were affected. Next, I'll be teaching you some rules to specify the configuration of a chiral center. Now basically, right, you need to know the ranking. Remember last time in alkenes, we talked about the E and the Z form. It is the same. The Kahn-Ingold-Prelog rule, the CIP rule. I hope you can still remember them. So what happens is now we are using this rule for a sp3 carbon center, and determine its configuration. Take note, not conformation but configuration. We are going via the atomic mass. So first of all, we assign the priorities on the 4 groups of a chiral carbon, and we orientate the molecules so that the group of the lowest priority, which we call number 4, points to the back of you. I mean, for me it's to the back, so closer to you, but for you is towards me. And then we look at the 3 remaining substituents. For the R configuration, from the highest to the lowest priority, if you do a rotation, if it is clockwise, it's R. If it's counterclockwise, then it's S. So basically, you see this molecule here. Okay, suppose we know that H, the white ball, is the lowest priority. So I send it back. I'm using from your perspective, so you push it to the back of you. Black is a carbon. And you see that this is orange, red, and green. Suppose we go by alphabetical order. Suppose this is number 1, 2, and 3. So what do you see? 1, 2, 3 is going counterclockwise, right? So this molecule here to you is S. To me, it's still S because when I do this from here, I'm going counterclockwise. So it's always S. But if it's the other way around, clockwise, then this molecule is R. Now for lactic acid, let's take a look. For this molecule here, H is always number 4 because it's the lowest priority. Carbon, carbon. So this is the highest priority, number 1. This is number 2, and this is number 3. Using this, we know that COH is a higher priority than methyl group. So now we push the H to the back like this, And we see that rotation from 1 to 2 to 3 is clockwise, and that's why it's R. And then for the enantiomeric form, this is number 4, this is number 1, 2, and 3. You see that it is S, because it's going counterclockwise. This molecule, please give yourself a try. This is actually S, because when you drive the wheel, right, you see that 1, 2, 3 goes counterclockwise. And for the bottom case, this molecule here, do some practice. This is again S, because when you rotate the 1, 2, 3, you still get counterclockwise. This example I'm trying to show you here is to illustrate that even though you have S in both cases, but you see this is S negative glyceraldehyde, the bottom is S positive alanine. So plus and minus have no link with S and R, totally no relationship at all, which means that I could have a plus, S plus, S minus, R plus, and R minus. No relationship at all. This is again another kind of a diagram to help you to see, push your number 4 to the back, and then you do the rotation, and then you do the rotation and see 1, 2, 3 goes which way. Is it clockwise or counterclockwise? That'd be easier. Now in class, maybe I can demonstrate to you in a much better way, because we have the connection there, a physical interaction, so you can learn better. But for now, if you can try and you do a few exercises and then you check answer, you got it right, that means you're all good. So this example here shows an R2-chlorobutane. I hope you use this method and get this right. That'd be perfect. Now what about molecules that have more than one chiral centers? Because we know that compounds are big. They contain so many carbons, and it is not uncommon to have more than one chiral centers. So the number of enantiomers that it has, there is a formula. It can have up to 2 power n. Take note, it can have up to 2. It doesn't mean that it must have 2 power n. Okay? For amino acids like threonine, there are 2 chiral centers, one on the carbon 2, one on the carbon 3. So 2 power 2 is 4. So we could have 4 possible stereoisomers. These are the 4. At the second carbon, it is a R configuration, third carbon R configuration. So it's RR. This is SS, RS, SR. These two are enantiomers because when you reflect an R, you get the S. When you reflect the S, you get the R at the same position. These two are enantiomers because R reflect give you S, R reflect give you S. So you see, these are mirror images. I just went through this with you. Now something called the diastereomers. They are stereoisomers that are not mirror images. Back to that example we talked about the previous slide. If we pick this and that, they are somewhat related, but what is the term to describe them? They are called diastereomer. Because now you have 2 chiral centers within the same molecule, but then now you only change one of them. So they are non-superimposable to each other, but they are not exactly enantiomers, and they are also not mirror images. So we call them diastereomer. I hope this shows you the true picture that you can understand. R and S flip, S and R flip, so these are enantiomer. R become S, R become S, so these two are enantiomer. But if you compare these, they're diastereomer. When you compare these, they're diastereomer. Alright. Epimers, another term here. It just tells you that there are 2 diastereomers that differ only at one chiral center, and all the rest are the same. So for these two, cholestanol and coprostanol, they are epimers because all the chiral centers are the same configuration except for one of them, carbon 5. For tartaric acid, you notice that it is a very funny molecule because it has 2 chiral centers, and when we draw this out in this manner, we have 2R, 3R, and 2S, 3S. And then when we do the other one, we have 2R, 3S, and 2S, 3R. But the thing is, for this molecule, we see a plane of symmetry. And recall that when a molecule has a plane of symmetry, it is not chiral. So what does that tell you? It tells you that these two are actually identical. they are the same. They are enantiomers, mirror images of each other. It means that all in all, tartaric acid only has 3 different stereoisomers because these two are identical. So we call them meso compounds. Meso compounds is what meso compounds. So meso compounds are compounds that contains chiral centers but still contains a plane of symmetry. So it means the overall conclusion is a compound can contain chiral centers but it could be overall achiral. Not surprising. For threonine, you have 2 chiral centers, 2 pairs of enantiomers, and a total of 4 stereoisomers because there's no kind of overlapping here. For tartaric acid, 2 chiral centers, a pair of enantiomer, and 1 meso compound, so in total you have 3 stereoisomers. For the plus and the minus tartaric acid, we know that they are enantiomers of each other. They have the same identical physical property like melting point, boiling point, and density. We went through this again, but let's drill it into you. And they differ in the sign of the rotation of the plane, polarized light. For the meso tartaric acid form, there's no mirror image relationship. So it's a different compound, and hence they have different physical property. So see that, right? The specific rotation is 0 because it is not even chiral. Melting point different from these two, different density, different solubility. Another term here, racemic or racemic mixture, we denote by using the opening parenthesis, put the plus and minus, put the plus and the minus together, plus on top of the minus, close parenthesis, or we can use the prefix D and L, D comma L, to show an equal mixture of the dextrorotatory and the levorotatory forms. Now this kind of mixtures shows no optical rotation because they have the equal amount of each, so it just rotate the same way and it cancels off. You see, it cancels off. Remember Louis Pasteur from France? So he began with a 50-50 mixture of the 2 chiral tartaric enantiomers, and then after that he did some chemical reactions and he was able to resolve the 2 different enantiomers by some physical separation. Now normally in the lab, when we want to separate the 2 enantiomers, we use something called the chemical resolution. So basically, the most common form is to use an acid-base reaction between the racemic of a chiral carboxylic acid and the amine base to yield an ammonium salt. Now, if we look at this example here, these 2 molecules are enantiomers. If we throw in an amine that's not chiral, we cannot resolve the product because the salt they form are also enantiomers. They have the same physical property, so there's no way to separate them. But if you throw in a base that has a chiral center, then you see this is R. When we throw in the R base, so they will have a different kind of structure at the end because now the salt, they are diastereomers which differ in physical property and hence can be separated. Remember what kind of physical property? Melting point, boiling point, solubility. So we always try to use a chiral base or acid to use an acid-base reaction to form different kind of salts based on the diastereomeric form and then separate them. So some charts for you to help you understand this topic better. A summary. Now isomers are compounds that have the same chemical formula but different structures. This is the main heading. We have got 2 main kinds of isomer, constituent isomer, stereoisomer. For stereoisomer, they are compounds which are connected in the same manner but different geometry, 3D arrangement. For constituent isomers, they are compounds whose atoms are connected differently, like branching, functional group isomers, positional isomers. Under stereoisomer, we've got 2 main kinds. One is enantiomer, mirror images, non-superimposable mirror image, RNS, lactic acid, and the other one is the diastereomer form, the non-mirror images. So under these, we have got cis-trans. Remember cis-trans? And configurational diastereomers. For this, we can use this term on the ring, cycloalkanes, or even in some alkenes. Thought for the day is you have to know that enantiomers of a chiral molecule have same physical and chemical properties, but will have different biological properties because of the chiral environment that it goes in. So the positive limonene, you can see from the name, right, has the odor of, or what I call it, smell. It smells good. Oranges, very annoying. Negative limonene has the smell of lemon. So they smell different, you know, the orange and lemon, but you see, they just differ by a simple chiral center. Alright, maybe you can copy down this mind map that I have for you. So, you know, for steric, some people ask me, steric, what's under steric? For steric, you have got torsional, 1,3 diaxial interaction, and gauche interaction. All these comes under steric. For stereochemistry, you know styrophones? Remember styrophones? You have positions right around your home, different sounds, surround sound. Stereochemistry. That's how the word comes about. Enantiomers. And the other side will be Diastereomer. And then the diastereomer, here of course we have got the E and Z, and then under it we have cis trans. So this is a subset of EZ. Maybe I can draw you another slide. Stereoisomer. Big mind map. We have got enantiomer. Some people see better with Venn diagram, so I just give you what I have. You can analyze it. This is the universal set. Subset enantiomer. Then we have got another subset, but of course these are not overlapping. Mutually exclusive diastereomer. And then under it we have got cis trans and EZ. And you see these are not overlapping because they have actually no link. But back to the previous slide, I need to put it below EZ because cis trans is very rigid. Thank you, I'll see you next time.